I think it's time to start. Okay. Good afternoon, everyone. Thank you for joining our MAS seminar. So this seminar series is mainly about topics in financial mathematics or fintech. So today we are very happy to have Dr. Bingyan Han to give us a talk about distributionally robust risk evaluation with causality, constraint, and structural information. So before the talk, let me briefly introduce you our speaker, Dr. Bingyan Han. He is an incoming postdoctoral assistant professor in the Department of Mathematics at University of Michigan. His research focuses on mathematical finance, especially model uncertainty, time inconsistency, and volatility models. His work appear in Finance and Stochastics, Quantitative Finance, SIAM Journal on Financial Mathematics, and so on. Previously, he was an assistant professor at the BNU-HKBU United International College. So he received his Ph.D. degree from the Chinese University of Hong Kong in 2020, and his bachelor's degree from the University of Science and Technology of China in 2016. So next, welcome our speaker, Bingyan. So now, Bingyan, thank you for sharing. So I think it's your turn. Thank you very much.
Thank you, Patrick. Thank you for your kind introduction, and thank you for your invitation to this talk. It's my great honor to give my research talk at NTU. Today, I'm going to talk about the problem related to model uncertainty. I'm going to use the optimal transport theory to study the risk evaluation problem. And in particular, I will focus on the temporal data. So I will introduce some causality constraints and the structural information. So the outline of my talk is as follows. After I introduce the framework, I will mainly use the duality theorem to solve the primal problem. In the duality problem, I will use the neural network to do the modeling, and to validate this idea, I will prove the sample complexity results and propose some optimization algorithms. After that, I will give you some numerical examples, which I found very interesting personally. Okay. During the talk, during the talk, if you have any questions, please just ask, and I'm very happy to answer any questions you have. Okay. So the problem I'm interested in is related to the so-called model uncertainty, but maybe the difference between risk and uncertainty are quite subtle, but their difference is quite important. So the risk, when we talk about the risk, we usually say that we don't know the outcome of the random underlying process, but we do know the probability distribution of the randomness. Okay, but uncertainty is different. And in the uncertainty problem, we also don't know the distribution that we are interested in. So we can take the example of flipping a coin. If we know the coin is fair, then we know that, okay, the distribution of the head and the tail, they are equal, and they have a 50% probability of head and 50% probability of tail. But uncertainty is more difficult. Uncertainty will deal with the problem that, okay, we even don't know the distribution of head and the tails. So it means that we don't know the probability of getting a head, the probability of getting a tail. Okay. So to handle model uncertainty, we have to consider several frameworks used in the literature. Typically, there are three frameworks that can be used to solve model uncertainty. The first framework is known as robust control. This kind of framework is used if, let's say, if the drift of our state process is uncertain. In this method, we will quantify the distance between two methods using the so-called relative entropy or KL divergence. However, one limitation of this framework is we have to use the methods with the same support. So the second framework if we are interested in the volatility uncertainty, so it means that, okay, I'm not sure about the volatility. In that kind of problem, we usually have two methods. One method is the nonlinear expectation, and another method is the Marquin-Volossov dynamic programming principle. These two kinds of frameworks can be used to handle the volatility uncertainty problem. Okay? In today's talk, however, I will focus on the third type of methods. This one is inspired by the optimal transport theory, and we will mainly use the so-called Wasserstein distance to handle the model uncertainty. The advantage of Wasserstein distance is we don't have to consider measures with the same support. Okay, so Wasserstein distance allows measures with different support, and also another advantage of Wasserstein distance is it has a very beautiful geometric interpretation, which will be shown later. Okay. So to introduce the optimal transport, we made a concept called coupling. Actually, the coupling is a joint distribution. Okay. Suppose I have the following problem. I have two probability measures. One is denoted as mu hat, another is nu. These two probability measures, they may have different support. Let's denote as x and y. I'm interested in the following problem. I want to reshape my original probability measure, let's say mu hat. I want to reshape this mu hat to the new probability measure nu. And I want to move the mass in the probability measure mu and to reshape this one as the new measure nu. So to do it, we propose to use a transport plan. Okay? So the transport plan is just the joint probability measure, and the mu hat and nu, they are marginals on x and y. Okay? We denote pi as the set of all couplings. Now we can interpret the function or the probability measure pi as follows. So pi xy will be the probability mass. We move from the original point x to the destination y. Okay, but in any transport, usually we have to pay a price or a cost. So let's suppose that if we want to move 1 unit mass from x to y, we have to pay a cost denoted as cxy. Okay. Then optimal transport or OT problem, it will find the most economic or the optimal transport plans. So in other words, we want to minimize the cost incurred by our transport plan pi. So we want to find the optimal transport plans over all possible plans. Okay. So in general, if we have some results, classical results, if the cost function is is good enough, let's say the cost function is lower semi-continuous, actually there is a theorem to guarantee that the infimum here will be attained. In other words, we can find a minimizer, which is the optimal transport plan. Okay. So intuitively speaking, we can interpret this OT distance as follows, or this Wasserstein distance as follows. It quantifies the difficulty of reshaping the measure mu hat to the measure nu. So in other words, it gives us a distance between these two probability measures. Okay. To use this kind of idea, we can introduce the model robust framework as follows. Okay. Typically, we have data observed from a real but unknown probability measure. So let's denote this one as mu. Mu is the real probability measure, but typically unknown by us. So we usually observe data from this measure, and using the data, we can construct a reference measure. So typically the empirical measure we can use. With this empirical measure, we can consider some problems. A fundamental problem we want to evaluate in this talk is, suppose that we are interested in the expectation in a form like this. F is the objective function we have. However, in many cases, for example, we don't have enough data, then this mu hat, this reference method is not so trustworthy. And maybe we don't believe in this reference method, and we think that, okay, other methods, they are also possible. So to incorporate the robustness, we will consider the evaluation not only on this reference method, but also on some methods that are close to this reference method in certain sense. And in this talk, we will first use the Watson system distance. So instead of working on method mu hat, we look at alternative methods nu, and the nu and the mu hat, they are close in the sense of Watson system distance. So the radius here we use is epsilon. Okay? And the worst case we look at is we take the supermum over all possible alternative methods that are close to mu hat. This worst case is the robust value we can obtain. Okay, so we call it the risk evaluation just for simplicity. Maybe in many cases we can take the negative sign, then it's the profit we are interested in. But here I follow the tradition that we call this one as the risk evaluation. Okay. Now this is the classic framework using optimal transport. And we don't have any structure on the underlying data X. However, in finance and economics, usually we have temporal data. So the data like the stock price, like the volatility, or the economic data, they are temporal in the sense that we have a structure in the data. So the data point X usually is X1, Xt, and X capital T. It's ordered with the temporal structure. If we look at the temporal data, now the transport plans in this set may not always make sense. So one restriction we have to impose is we cannot use the information from the future. Okay? So suppose today is time t, then I cannot use the information from tomorrow or from the day after tomorrow. So in the mathematical finance or in the stochastic calculus, we actually have to impose the adaptiveness on the transport plans. Okay? Mathematically, we should impose the following condition on the transport plan. Suppose today is time t, and the data, the distribution of y should only depend on the distribution of x up to the current time. Okay? So the data point y cannot use the future information of x. So the future information here means the information from t+1 until capital T. So this one is reasonable because you know that we have to follow the adaptiveness in the transport plans. This kind of condition is known as the causality condition. But however, I think the notation here is somehow equivalent to the adaptiveness. It's actually talking about the adaptiveness on the transport plans. Okay, so we call the transport plans that are satisfying this causality condition as causal optimal transport. So instead of minimizing over all possible transport plans, now we only minimize over the causal optimal transport. Okay, so if we consider the same methods mu hat and nu, we can roughly think that okay, this set should be smaller than the original transport plan set, and the infimum here will be somehow bigger than the original OT problem. Okay, now we can again look at the robust risk evaluation problem. And now we only look at the causal optimal transport plans, and the causal Watson system ball is given by this one. Okay, because we consider few transport plans, so this supermum somehow will be smaller than the original OT framework. Okay, so for simplicity, I call this one as the COT risk evaluation, and the previous one as the OT evaluation. Okay, now in this primal problem, you can see that we have, in general, we have infinite many alternative methods, which is not easy to handle. So that's why I have to go to the dual formulation, which is easier to solve. Okay, so now I want to present you the duality results. As a preparation, we need to impose some technical conditions. So roughly speaking, in the first assumption, we should look at the methods that are good enough. Somehow we need to impose the continuous condition on the reference methods and the true method. The second assumption is on the objective and the cost function. We impose some semi-continuous conditions on them, which is quite classical in the optimal transport theory. Okay? A remark is, under these conditions, at least we can have the infimum of COT. So it's the technical conditions we meet. As a preparation, now compared with the OT formulation, the only difference is we have to impose the adaptiveness. The problem is, how can we formulate the adaptiveness in the dual formulation? The key observation here is, actually, this causality constraint is equivalent to a linear constraint. Okay? It's not so complicated. So we introduce a test function space, denoted as gamma. Gamma contains the following function. It has a shape like h multiplied by g. Let me give you an interpretation here. Y is the alternative method we have, and x is the reference method we have. Okay, so J here yields the whole path of the x, and then minus the conditional expectation up to time t. So we can interpret this difference of G as the information from the future. Okay, because this one we have already minus the current information available, so the difference between them will be the information from the future. Okay, H here we can think H somehow as our control. So we can, let's say we can do the trading, we can formulate our operation using H depends on the value of Y up to time t. Suppose that my transport plan is using the information from the future. Then I can find the strategy of the control, in this case, the function H and G, to punish this kind of usage of the future information. Or in other words, I can find the H and J to make this integral to be non-zero. Okay, so there is a result that we can reformulate this causality constraint as a linear constraint, such that pi is causal if and only if for any test function gamma, this expectation equal to 0. Okay. Now, with these results, we can formally prove the strong duality results in this theorem. So the primal problem will equal to the dual problem, and the dual problem is given by the following form. So let me give you some remarks here. From this duality form, you can see that now we don't have to deal with infinitely many alternative methods. We only have to deal with the reference method mu hat. Okay? In this formulation, we only have a mu hat here. The objective function somehow is modified. Lambda is the Lagrange multiplier, and the gamma is our test function. We have to take the infimum over all possible test functions. So another remark is, so suppose we don't impose the causality constraint, then we can recover the OT formulation in the following way. We just take gamma to be 0. If we take gamma to be 0, then this duality result will be the classic OT formulation. Okay. And also here we can see that the problem involves the infimum and the supremum. So in general, it will fall into the minimax optimization problem. Okay. Now, before we move on to the theoretical results, I want to give you one concrete example. This comparative example is quite simple. So the major objective is to show you the difference between OT and the COT formulation. Okay, so consider the following example. Let's see that we only have 2 time steps. Another domain is the interval given here. The reference method contains 2 sample paths. One sample path is from 0 to 1. Another sample path is from 0 to -1. We have 20% probability of the first pass and 80% probability of the second pass. So equivalently, we can think that at the time 1, the value of x1 will equal to 0 with probability 1. And in the second step, we have some uncertainty or some risk. And with 20% probability, we will take a value equal to 1. And with 80% probability, the value is -1. Okay. We consider the cost function, which is a little weird. However, the motivation behind it is I want to force y to use the future information of x, so it can show you the difference between OT and the COT. So we take the cost function here as follows. It's the indicator function of whether x2 equal to y1. And the x here, I omitted the time script. So x here means x1, x2. Y here means y1, y2. If x2 is not equal to y1, then it takes the value of 1. The objective function f here equals to x1. So it will only focus on the first coordinate. And we use the radius of the y-system ball equals to 0.2. Now, we are ready to calculate the worst case measure. For the OT formulation, we can calculate the worst case measure using the duality theorem. And we find that the worst case measure from the perspective of OT, let's think that the worst case measure is given by that y1 always equal to x2. If y1 always equal to x2, definitely y1 will use the future information because it's using the information from the second step. It's using the value of x2. It will not incur any cost because we always have y1 equal to x2. So the cost here will be 0. And the worst case value, we can see that if y1 equals to x2, so we have 20% value equal to 1, 80% equal to -1. So the worst case value will be 0.2 plus 0.8 multiplied by -1. So the worst case value we have should be -0.6. However, COT will be different because COT cannot use the information from x2. He can only use the information from the first time step. But if we look at this example again, if we stand at time 1, we can see that x1 is not useful to predict the value of x2 because when we know x1 always equal to 0. So x1 is not useful to predict the value of x2. Then the only information we have is we can only use a constant to find the worst case scenario. So COT will find the worst case scenario as follows. y1 is always equal to -1. And you can calculate it in the following way. If y1 equals to -1, we will find that the cost function will be non-zero only when x2 equal to +1. And we also say that x2 equal to +1 with probability equal to 20%. So it's still in the y-system ball. Because y1 always equal to -1, then the worst case value we have is -1. So you can see that these two values, they are quite different with each other. In general, actually, we can prove that their values can be arbitrarily different. Their difference can be quite large. So in this example, the one conclusion we have is OT and COT, they can really have different optimizers. And the OT somehow, I think it's not reasonable to use OT if we consider temporal data, because now you can see Y1 use the information from the future. So it's too conservative in certain sense. When we build the worst case scenario, we can only use the current information to find the worst case scenario. So we don't have to use the information from the future to find the worst case method. Okay. Somehow for another side, okay, you may wonder, in certain cases, maybe OT and COT, they can have the same solution. I prove the following result. Okay. Suppose that our objective function is separable and our cost function is also separable. Then we can prove that, okay, COT and OT, they have a common optimizer. Or in other words, they have the same primal value. So one example we can consider is maybe we are interested in the sum of y, and the cost function we use is the L1 distance. Then the worst case scenario actually is explicit. The worst case scenario is just the reference measure shifted by a constant. This constant will depend on the radius of the ball. So if the radius is bigger, then we shift the reference measure bigger. But this kind of result motivates to consider the problem one step further. So it shows us one limitation in the OT and the COT formulation. Okay, so if I have reference, if I have temporal data, and we find that in this I think quite a simple case, we find that the worst case scenario, it relies on the reference measure pointwisely and pathwisely. So the worst case measure just shifts the reference measure by a constant. It will shift the path point by point and path by path. So COT and OT, they will not look at the sample data jointly. They just look at the data one point by one point. If the data have some noise, then COT and OT will also observe the noise. So this feature is somehow conservative and undesired. That's why we want to further restrict, maybe we want to further restrict the alternative methods. So maybe we don't have to consider all the methods in the water system ball. So if we have further information, maybe we can impose the conditions on the water system ball to restrict our choice. So it motivates us to consider the structural information given here. Personally, I call it SCOT, as for the structural information. Suppose that I have some priori information. Maybe, for example, the volatility problem. Maybe I have a model, and I believe that the volatility should follow this parametric model. Then I can incorporate this priori information in the following way. We further assume that the alternative measure will be in this parametric space. So when we take the supermum of alternative measures in the water system ball, we also restrict the choice to be in this parametric space. Okay, so I call this one as the structural information, and it will depend on the problem we are considering. So later on, I will show you several examples. How can we incorporate the structural information into the formulation? Okay. If we are considering this SCOT, we can also prove the duality result. So the primal problem of SCOT will equal to this duality value, and it can be solved in the following equation. Now, let me give one remark here. So it looks a little complicated. We have the supermum over the alternative measure in the parametric space, infimum over the test function. But inside, we also have a supermum over the transport plans. However, this one is quite easy to handle. In the inner supermum here, if you still remember the definition of water system distance or the optimal transport, actually this one is it's calculating the water system distance using the cost function given by these two these three functions here. So we have some algorithm available to calculate the supremum inside in this dual formulation. Okay. Now we are ready to introduce some methods to solve this problem in the dual formulation. But you can see one major difficulty is in the test function. Gamma here is infinite dimensional because we have to consider all continuous and bounded functions. So gamma will take any continuous and bounded functions. The space here is infinite dimensional, which is the major difficulty we have to overcome in this problem. My idea is to use neural networks. Okay, we use neural networks to model the elements, the continuous and the bounded functions from the test function space. The motivation is the celebrated universal approximation theorem of neural networks. We know that, so suppose we use a wide enough neural network, we can approximate any good functions in certain sense. So of course, neural network is not the only way to solve this problem. Somehow we can also consider the linear programming, or we discretize the space and use the linear programming method to solve this problem. But the disadvantage of that method is it usually suffers from the curse of dimensionality. Neural networks can handle this kind of problems with large data sets, and it will be easier for us to handle the problem with a big data set. Okay? To validate this idea, I pose a theoretical result, the sample complexity of COT and SCOT, using a mathematical tool called the Rademacher complexity from the machine learning theory. Okay. Now, let me show you the idea of the sample complexity. Before that, there's one technical difficulty in the relevant proof. The classical, usually we use the empirical method as the reference method. But if we are dealing with temporal data, the reference method, the empirical method here, is not consistent in the weak sense or in the persistent sense. Why we have this technical difficulty? You can think the problem as follows. So suppose the real method has a density function, or in other words, it's continuous. Then we can draw the data from this reference method mu, and with probability almost equal to 1, we will definitely observe the sample paths different from each other. Okay, so for example, at time 1, at first I draw the data, I observe a value equal to 0.5. If I draw the data again, then I will definitely observe a data different from 0.5. Okay, so the probability that two observed sample passes coincide with each other is 0. It gives us the difficulty because if we know the starting point, then the whole path is known. So we don't have any adaptiveness in this case, and the convergence in the persistent distance will fail. Because so if we have two passes, they are different with each other, and I know the starting point, then I know the whole path. So I can distinguish between these two paths by their starting point. So we don't have any causality or the adaptiveness in this case. So this one is the reason why we lost the consistency if we use the classical empirical method in this problem. To handle this kind of problem, recently, Bakerhoff and his co-authors introduced a quantization idea. So we can use the so-called adapted empirical method and then maintain the consistency. The idea is given as follows. Let's further restrict to the following situation. Suppose the support of our transport plan, the support of our method is a closed subinterval. And we introduce a participation map that's denoted as phi n. This participation map will divide the interval A from A to B into disjoint unions and with equal length. So phi n will map each subinterval to its center. Okay, so let me show you one figure to get the idea behind this adapted empirical method. Okay, consider the following figure, and suppose we have 4 time steps. This is time 1, 2, 3, and 4, and we observe the data in discrete time. The black dots shows us the observations, the real value. Maybe at time 1 we observe this one, and time 2 this one, and time 3 this one. Okay. The adapted empirical method will do the following transformation. Suppose we divide the interval into the following subintervals. Maybe this one is from 0, 1, 2, and 3. So we divide the subinterval as from 0 to 1, 1 to 2, and 2 to 3. Okay. So we map each observation to the center of the subinterval. For example, for this point, it's not at the center of the subinterval 0 to 1. We map it to the red point, or in other words, we quantize this point. So this one will be mapped to the center of 0 and 1. So it will be mapped to 0.5. Similarly, for the second time step, we map this observation to the center of the interval 1 to 2. So maybe this one is 1.5. Okay. After we do the mapping one by one, we use the adapted empirical method with the red points instead of the black points. Now, you may wonder why it will resolve the problem of inconsistency. So, roughly speaking, the reason is, so let's see, in this interval, maybe the real observations, this one maybe is 0.85, and we observe another data point, maybe 0.2 or 0.3. So they have different values at the beginning, but after the quantization, all of them will take the same value given by 0.5. And with this same value, we cannot distinguish between the path of 0.8 and the path of 0.2. So all of them will take the value as 0.5. Then we cannot distinguish between these two paths with only the first step, the value of the first step. So it can resolve the problem here. So now, if we know the starting point, we do not necessarily know the whole path, and the convergence in the Waterstone distance somehow can be maintained. If we have enough data, we will divide the subset smaller, and we can let the length of the subinterval to go to 0. Then we can recover the consistency in Waterstone distance. So this is the motivation behind why we should use the so-called adapted empirical method instead of the classic empirical method here. Okay. With this adapted empirical method, we can use the Rademacher complexity. In the language of machine learning theory, they usually call the parameters that we can minimize as a hypothesis set. Okay, so the test function h and j, and also the Lagrange multiplier, they will be called the hypothesis set in this in the language of machine learning theory. Okay, recall that our dual problem want to minimize the following function, and I use the adapted empirical method here. So if we take the hypothesis set as the whole test function space together with the Lagrange multiplier, then we can recover the dual problem perfectly with the adapted empirical method. Okay. Now, the first result we have is as follows. In the left-hand side, the dual value with the real probability method mu And the difference between this value with the dual value using the empirical method or the data points, we want to bound this difference between the dual value of the real method and the dual method under the empirical method. So if this lemma tells us they will not be far from each other, their difference will be bounded by the Rademacher complexity of the functions. So now we can hope that, okay, suppose we have enough data, suppose the sample size of the data goes to infinity. If the Rademacher complexity can also go to 0, then we can actually find that, okay, these two values, they are equal to each other. Okay? So luckily, we have some known results from the deep learning community. Let's say if we use the fully connected neural networks, in this paper, they prove that the Rademacher complexity will converge to 0 in the order of 1 over the square root of the sample size n. Similarly, if we want to use the recurrent neural networks, there is also a result, and the order of convergence is the same. Okay. Now we can hope that, okay, because Rademacher complexity will converge to 0 when we have enough data, then this dual value under the real method and under the empirical method, they will equal to each other, okay, which is desired by us. Okay. Now we can formally prove the lemma given as follows. Given a hypothesis set or given a set of parameters, although I put it here as the assumption, but it actually is an assumption on the neural networks we are using. So we have some guarantees to make this assumption hold. And we can obtain the following results. Let the sample size go to infinity, then we will recover the dual value. And this dual value is the infimum over the parametric set over the hypothesis set at theta k. Now, in the second step, we can let this hypothesis set to converge to the test function space. So the test function space we have is the whole is the Lagrange multiplier together with the test function space we introduced as gamma. Now, after we take this limit, we will recover the dual value, which is also equal to the primal value. Okay, so this results guarantee that, okay, we can use neural networks. If we can find the infimum here, then we can recover, we can find the dual value together with the primal value. Okay, so it's the theoretical guarantee that we can use neural networks to solve this problem. Okay. As a side note, we also have some finite sample guarantee. Okay, so suppose we don't want to take the limit. I only have a finite sample. This result tells us, okay, if we denote J star as the real risk we have, and this risk is under the real method mu, and the value we obtained using the finite sample, which is denoted as Jn hat. This dual value actually is an upper bound for the J star here, okay, with a very high probability. Okay, it's the finite sample guarantee we have. Okay, now, so the problem becomes, how can we find the infimum here? How can we find the infimum over a set of parameters? So we introduce the algorithms as follows. For the COT, we have the following algorithm. Recall that we have the infimum, we have the supremum. So we have two loops here. So for the inner loop, we maximize over the alternative scenarios Y with the method of SGD or the stochastic gradient descent. For the outside loop, we also minimize over the Lagrange multiplier and the neural network, the test function. So we use the Adams method in the minimization. Okay, this is the algorithm for COT. For SCOT, somehow the algorithm is quite similar. The only difference is we also have to calculate the supermum over pi. So if we look at the function here, we have three optimizations here. We have to calculate the supermum. The supermum here actually is calculating the Wasserstein distance. After we obtain the value here, we can take the supermum and the infimum using the alternative gradient descent. Okay. So for the supermum over pi, it's calculated with the so-called Sinkhorn algorithm to approximate the Wasserstein distance. Okay. Now we can look at some examples, okay, from finance. Okay. The first example I am interested in is a simulation study, okay, on volatility. Suppose we want to do some trading related to volatility, and we are concerned about the average level of the volatility over a certain time period. Because it's a simulation, so let's assume that, okay, the real process or the true process is a so-called Jacobi model. This one is an extension of the Heston model, but it is bounded. It takes a value within this interval. Okay, Jacobi model is continuous. So in the simulation, I will discretize the SDE and use the samples from the discretized SDE. Okay. Now, the key part here is how can we incorporate the structural information to the modeling. Let's do the following thing. Okay. Suppose the decision maker also knows the true model is Jacobi model. Okay. However, he doesn't know the parameter, the real parameter. So he will use the algorithm to calibrate the parameter kappa, phi, and sigma. And finally, the decision maker will believe in the alternative model with certain probability. Okay. So with probability like 50%, it will believe the sample from the alternative model. And with probability 1 minus p, it will believe in, he will believe in the sample from the reference data. Okay. So now the objective function is the sample mean. And in this numerical example, we consider the quadratic cost function. This table gives us the simulation result. Okay. Actually, if we use the OT formulation with a sample mean as the objective and the quadratic cost, actually the result is explicit. We can solve it explicitly. However, I want to use the algorithm to test whether it will convert to the theoretical value. We can find that, okay, when the true mean level is 50%, or the volatility is 50%, and this is the real mean we have. Then the simulation, the worst case, and the OT formulation will say that, okay, he believes in that the worst case level will be roughly 72%. If we incorporate the structural information, SOT means that I use OT formulation together with the structural information. Then we restrict the alternative scenarios. So we look at fewer alternative methods, and we can see that the dual values are smaller, which is reasonable because I only look at fewer alternative methods. Okay. If we further consider the causal optimal transport, we can see that the dual value is also smaller, even smaller than both of them. Okay. Another difference between these three methods is we can see that in OT, the dual value will not change if we use different time steps. But for SCOT, it's different. If we use annual data, semi-annual data, if we use daily data, then SCOT will obtain somehow different worst case. So in other words, SCOT will appreciate the difference in time steps, but OT will totally ignore this difference in time steps. Okay. And another interesting finding is the bimodal phenomenon in the in the simulation study. So let me explain this phenomenon in details. I repeat the code in 50 times. So I can obtain 50 pairs of SOT and SCOT values. So I can calculate the difference between SOT and SCOT, and I obtain 50 differences. So I plot the histogram, and we find that, okay, for about 20 instances, the difference between SOT and SCOT is quite small. Okay, in other words, SOT and SCOT somehow they obtain very close values, or in other words, Causality didn't not punish the violation of adaptiveness. But for more instances, like 30 instances in this programming, in this simulation, they have SCOT has a smaller value and SOT has a higher value. Okay? This bimodal phenomenon actually tell us it's quite important to impose the quantization method or to use the adapted empirical method, because sometimes we are not lucky to observe sample paths that are close to each other. So if we don't use quantization, they will be distinguished even after the first time step. Then there will be no punishment from the test function. That's why SOT and COT, they obtain the same value for almost 40% in this simulation. Okay, so this phenomenon is related to the quantization problem, and also it reminds us to use a larger data set. So then this bimodal phenomenon will be resolved somehow. Okay. So in the next few slides, let me show you some sample paths obtained as the worst case scenario. So first, let's look at the OT formulation. As we mentioned before, the worst case scenario obtained by OT is just the reference path shifted by a constant. And you can see that the worst case scenario in OT is parallel to the reference path. And the temporal structure between the worst case scenario and the reference scenario, actually they are the same. Okay? So there's no difference in the temporal structure. So it will decrease at the first step, it will decrease also at the first step, both in the reference method and in the worst case scenario. So that's why I believe that OT is quite conservative in this sense. It did not obtain any meaningful temporal structure that are different with the reference case. So it's just shifted the sample path by a constant, and he believes this one is the worst case scenario. So it's restrictive because let's say if there are some noise in the reference method, then our worst case scenario in OT will observe, will also use the noise in the reference method. Okay? So that's why OT formulation in this case, it's not so meaningful and also quite restrictive in this case. Okay? However, if we use structural COT or SOT, we can obtain quite a different temporal structure between the worst case scenario and the reference scenario. So we can see that the temporal structure of the worst case scenario shown as the green line and the orange line, they are quite different with the reference case. Okay? In this one, we consider the semi-annual data, and SCOT, SOT, they believe that the worst case scenario will be as follows. The worst case scenario will be the situation that we have a very high level of volatility during the whole time. So the volatility level is much higher than the real mean 50% in this case. So SCOT believes that it should be the worst case compared with this one. So OT believes that, okay, this one is the worst case, and the SOT thinks that, okay, this one should be the worst case. Okay. In this figure, so this one we consider the semi-annual data, but in this one, let's consider the daily data. if we consider the daily data, SOT and SCOT, they obtain different worst case scenarios. In this situation, they believe that, okay, the worst case scenario will be like this. If we have the volatility increasing significantly with the time, so this one will be the worst case scenario because we are taking the superminimum. So if we have the following observation that the volatility is increasing significantly, this one will be the worst case. Okay. Now we compare these two figures, we can see that okay, SOT and SCOT, they can find different worst scenarios if we have different time lengths, different time steps. So it's the first simulation study. In the second example, I'm interested in a problem with empirical data. So suppose that we want to find the upper bound of SP 500 index in certain period, maybe next day or next week. And to formulate this problem into our framework, we made a function f. And this function should be able to predict the next return based on the current information, like the current index level, the current economic data. Of course, this function f is not obvious. I propose to model this function by a fully connected neural network at first. Then we fix this objective function f and generate the alternative scenarios using the residual network from computer vision. I use the residual network mainly for the following reason. Okay? Residual network is closely related to the identity network. Let's say if the reference method is the worst case, then the residual network will just output the reference data. If the data, if the residual network thinks that some data that are close to the reference data, they are the worst case, then residual network can generate the data close to the reference method. Okay. Let me show you one figure to see the difference between the formulations we have. Okay. In this figure, we show the following out of sample testing. We have 100 trading days in total in the horizontal axis. And recall that I want to give an upper bound for the return in the next period. So I use, maybe this is not, this is too small. So let me show you that the black line here, the black line is the difference between the benchmark and the target return. The benchmark will only use the function here. So there's no robustness in the benchmark. The benchmark will simply use the function we learned here, the f we use here. And you can see that the benchmark minus the target somehow is, in certain cases, it's bigger than 0, but in some cases, it's lower than 0. It means that, okay, benchmark didn't find the upper bound, especially at the last 20 periods here. And the orange dot gives the difference between OT predictions and the target. And you can see that OT predictions are quite aggressive, especially for the part given here. For example, during this period, the OT prediction overestimates the return. And it's quite aggressive. The return is, the upper bound is quite aggressive. But if we compare these results with our SCOT framework, we can see that, okay, our SCOT framework are better because it can appreciate the problem that we want to find the upper bound, but we also don't want to be too aggressive. So we can find the upper bound, but at the same time, we can maintain the error to be small enough. Similarly, for this part, you can see that OT here underestimates the return in the period given here. And our framework SCOT also performs better at this part. It gives the upper bound, although this one is not so, this one is still negative, but this one is better than the OT formulation. Okay, so remember that all of them are out of the sample, so there's no overfitting problems. So we are considering out of sample problems here. Okay, from this figure, I want to say that okay, SCOT somehow is better than OT in this problem. Okay. Now I want to conclude the talk with the following remarks. In this problem, I proved something, but there are also some problems that are left open. In particular, the problem left open is the convergence analysis. We are using SGD to deal with the minimax optimization. The problem is non-convex and also non-concave. So the convergence analysis is quite hard. As far as I know, there is no results for right now for this problem. So usually they have to assume the problem to be concave, and they allow them to be non-convex. But non-convex and non-concave is little known by us. The second problem I didn't consider in this talk is so that maybe the decision maker can control the underlying processes. And if we have control, I think there are also some problems that are quite interesting to be solved. The preprint in this talk is available online. And also I will release the code later. So I think that's all I want to say in this talk. And thank you very much for your time. If you have any questions, please ask. I'm very happy to answer any questions. Okay. Thank you very much.
Thank you, Bingyan.
Thank you.
Okay, so let's come to this Q&A session. Let me check with the audience. Do you have any questions or comments for our speaker, Bingyan? So please feel free to unmute and just ask. Okay, perhaps I first ask a quick question,
Sure.
maybe even a naive question, asking for your insight about the formulation. So you also introduced a few formulations about the robustness, including the volatility, uncertainty, and also here you use the Wasserstein distance and optimal transport to characterize the robustness. So do you think which one will be more conservative, or how do you compare them?
I think the difference between these frameworks are as follows. So for the robust control case, this one can only deal with the probability measure with the same support. But yes, somehow the relative entropy is not a distance. It's not a symmetric. So the distance between A and B is not equal to the distance between B and C. B and A. A and B and B and A, they are different. To see which one is more conservative, I don't have a quick answer for that. But I think that Wasserstein distance is attractive in the sense that it can handle the probability measure with the same support, with the different support in a unified way. Okay? And also, if we want to see which one is more conservative, it highly depends on the radius we use, the epsilon we use. Yeah, so somehow if we have some method to choose a better radius, maybe one framework can achieve a better result than another. So the radius will be quite important in most situations. Yes.
So maybe some of just share some of my opinion here. So if we apply the framework to risk measure, just like Peng did with his framework G expectation, to characterize the G VAR or some other risk measure, then we may have some objective to guide us to choose the radius of the washer-string distance. I mean the radius for the washer-string distance. That may be helpful because I think after all you still need some objective to guide your robustness, something like that, right? So okay, great. So I see this word is quite tedious. And let me check with the audience again. Any questions? Any comments? So if you have maybe further questions after the talk, I believe Bingyan will still be very happy to take your question, and you may send him email. I believe you can just simply Google search his name, then you will be able to find his contact. So if there is no further questions, then let's thank our speaker again. So thank you very much, Bingyan. Okay, so I'm going to call the end of this session. Thank you, Bingyan. Thank you all the participants of this session. Thank you very much.
Thank you.
Thank you. Bye-bye.
Bye.